Well, we start this video with a quick summary of whatever we have seen in the last video. Namely, I have a circle, just the circumference, not the disk, and on it I am trying to put a measure. So the measure is going to capture the idea of arc length, or you might say probability of picking a random point, or you might say just length of a subset of the set S. So here are the general conditions. Mu, that's a measure, is defined on all subsets of S. It's a non-negative number, real number, with the obvious condition that if you have disjoint countably many sets, then this will add up. Then the specific thing that I want here in order to capture the intuition of length is that, first of all, I will assume that entire length is 1. This 1 is nothing very important. Whatever is the entire length, without loss of generality, I will take it to be 1. And then the important thing is that if I give you some set here, and if I rotate it, then the length we cannot change by rotation. So take any subset A of S, take any rotation, I just write rot, then length of A is same as length of rotated A. On A you apply that rotation, whatever that is, the length must not change. What I am going to show is that there does not exist any function mu which satisfies both the conditions. And that is shocking, because this is intuitive, and the two intuitions clash. I am going to show that. Now in order to do that, what I will first do is I will start with my S, that's my S, and I am going to open it up. So I will just break it at some point. You break it. And now it finally becomes just an interval. Now I will consider this interval as 0, 1 to fix up ideas. So since I said the entire length is 1, so I can consider as if it starts from 0 to 1. So every point here is actually a point here. I am just writing it as an interval so that we can think more easily. Now I am going to define an equivalence relation for points in this set. So if I give you this point and I give you that point, call it x and y, I shall say x is equivalent to y if x minus y is a rational number. So 0 is equivalent to half, 0 is equivalent to 1, all the rationals are equivalent. Similarly, 1 over root 2 will be equivalent to 1 over root 2 plus 0.1 and things like that. But 1 over root 2 is not equivalent to 1 over root 3. Now whatever is going to follow, I will just consider my set S as something like a Venn diagram, just to fix ideas. So it is the same thing, same circle. Sometimes I am thinking of it as a line, now I am thinking of it as a Venn diagram. So now that I have got an equivalence relation, so if I take some point here, it is equivalent to some other points, so I can get a partition of my set S. So in the original thing, you were basically getting some point, this is one equivalence block, these are all equivalent, like all the rationals. Then all the rationals shifted by the amount 1 over say, root 2, they form another equivalence block like that. So I have got lots of equivalence blocks. Whenever I have equivalent relationship, I will get this partition. What I shall do is I will pick one representative from each my partition. So one representative from each partition, and I shall call the resulting set M. So M has exactly 1 point from each partition. So if you take two elements M1 and M2 in M, then you know that M1 and M2 are not equivalent because they lie in two different equivalence classes. So if M1 is not equal to M2, then they cannot be equivalent either. Now just observe one thing, that rotation is basically like adding a number modulo 1. So if I take this and I rotate it, I am just adding a number. Say I add 1/3, then I move here. Now what happens if I add 1 with it? It rotates all the way and comes back to itself because the total length is 1. That is why I said modulo 1. If I add 1.5 with it, first you come 1 and then you move only 0.5. So you only look at the fractional part. The integer part will always bring you back to your original position. So with this understanding that this geometric concept of rotation is here nothing but adding a number, and whenever you go out, so when I consider this as an interval, whenever you move out here, you basically come back to the other end. Okay, so now I had this set M. Suppose with this M I add the number 1/10. I claim that this thing and original M cannot have any intersection. And the reason is obvious, because suppose there is some intersection, in that case, there is a point which is here and there is a point which is here. So suppose I take that common point, which is in both the cases, so you will have some point M1 plus 1/10 equal to some point here M2. So M1 and M2, which are distinct points, at the same time they differ by a rational amount, which means M1 and M2 must be equivalent, and that contradicts the fact that if I take any two elements of M, they cannot be equivalent. Using the same technique, you can see that if I take two distinct rational numbers R1, R2, you rotate M by M1, you rotate M by R1. Whenever I say this plus, you mean just rotate it by R1, so I have the modulo 1 thing, I am just writing it as plus. And if you rotate M by R2, then these two sets must be disjoint, because if there is anything common, in that case that you get two elements of M that will differ by an amount R1 minus R2, which is rational. And similarly, directly from definition of M, we have this: you take any point X in S, then there is some rotation R such that X will be in that rotated version. And why is that true? Because if X is in S, then this X naturally lies in some equivalence block. So in that equivalence block, you will have some representative of M, because M has one representative from each equivalence block. So X has something which is in M, and what you do is that you just pick up that particular rotation which will allow this M to come to X. So you have X minus M must be some rational number R, because they are equivalent, and you just choose that R. So everything in S can be covered by some amount of rotation of your set M. Now suppose I take all the rationals in close 0, open 1, R1, R2, they are countable, and you apply the appropriate amount of rotation to M to get your sets AI. Then what I see is that AI satisfies this condition. They are all disjoint, that's what I proved just now. And I also see that union of AI must be equal to your entire S. Right? Now you get a contradiction. The contradiction is simply this: you say that your mu is defined for all subsets of S, so in particular it must be defined for M also. So what is your mu M? Mu M must be some non-negative real number. Suppose I ask you, can mu M be equal to 0? If mu M is equal to 0, then because you said that after rotation the measure cannot change, so each of your AI must also have 0. So mu of AI then must also be 0, because AI is just a rotated version of M. Now these are disjoint and their union is S, which means mu of S must be sum of 0, 0 plus 0 plus 0 plus dot 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 dot. So this also must be 0, and that contradicts the fact you have assumed mu of S equal to 1, which means mu of M cannot be equal to 0. So if it is not 0, it has to be strictly positive. So let's see if it is strictly positive. Whatever it is, suppose I call it something epsilon, strictly positive, then all these things must also be epsilon, because it's just rotated, which means this series now becomes epsilon plus epsilon plus epsilon plus epsilon, which forces this to be infinite, and again a contradiction, because mu S was supposed to be 1. So it cannot be 0, it cannot be positive, which means mu of N cannot be defined within this setup. And that's a contradiction which proves that there is no mu which satisfies both this condition.